When you point an infrared thermometer at a coffee mug and pull the trigger, a red laser dot appears on the ceramic surface. It's easy to assume this beam is actively grabbing the temperature and reflecting it back to the gun. In reality, that red dot is a separate targeting aid. It is a simple diode laser that helps you aim, but it plays no part in the actual temperature measurement, which happens through a process invisible to the human eye. Every object around you right now, from your wooden desk to your hot coffee and even your own skin, is constantly glowing. You simply cannot see it because the light is being emitted in the infrared spectrum. This effect occurs because of black body radiation. This principle states that every object in the universe above absolute zero, minus 273.15 degrees Celsius, contains vibrating molecules that release kinetic energy as light. This chart illustrates the Stefan-Boltzmann law. It shows how rising temperature leads to a massive increase in infrared glow intensity. Because energy increases to the fourth power of temperature, even small heat shifts create significant changes in emitted light. The device in your hand functions as a specialized digital camera designed to photograph and quantify this invisible heat radiation. To understand how it captures that glow, we have to look past the plastic housing and the decoy laser diode. The first obstacle is the lens. Standard glass blocks infrared light, which makes traditional camera optics useless for this specific task. Instead, the thermometer uses a specialized lens made of materials like polyethylene or germanium. These materials are transparent to infrared energy, allowing the glow to pass through. This cross-section shows the lens gathering scattered infrared photons and funneling them inward. Photons are the elementary particles that carry electromagnetic radiation, including this invisible light. The lens is shaped to concentrate those photons onto a single microscopic point deep inside the thermometer's sensor path. Without this specific lens material organizing those scattered photons, the infrared energy would simply bounce off the thermometer's casing, leaving the sensor in the dark. At that focal point sits the heart of the device, the thermopile. A thermopile is an electronic component that converts thermal energy into electrical energy. Inside the thermopile is a stack of individual thermocouples. A thermocouple is a junction made of two different metals that produces a voltage when there is a temperature difference between them. This process is known as the Seebeck effect. As focused infrared light heats the top layer of the junction, the difference in temperature creates a microvoltage that flows across the metals. The hotter the object, the more infrared light it emits, which generates a proportionally larger electrical signal across the sensor. This tiny signal is processed by an analog-to-digital converter, a chip that translates electrical fluctuations into data, and a microprocessor. The device compares the signal to its own internal ambient temperature and factors in the data to reach a final result. The thermometer does not feel heat. It translates invisible light into electricity, and electricity into a digital number on the screen. Even with this precise physics, the thermometer can be easily fooled. Point it at a shiny metal pan, and it will often provide a wildly inaccurate reading. To give an accurate number, the device must account for emissivity. Emissivity is a measure of how efficiently a specific material radiates its own internal heat into the environment. This illustration shows a high emissivity object, like a matte black pan on the left. It acts like a light bulb, honestly radiating its true internal temperature directly toward the sensor. On the right, the polished pan has low emissivity. It acts like a mirror, trapping its own heat inside while reflecting the infrared energy of the room or your own body back at the lens. When you measure a reflective surface, the lens captures this reflected bounce rather than the object's actual temperature, which provides a false reading to the microprocessor. Every reading is an attempt to capture a delicate, easily manipulated snapshot of the universe's invisible glow.